Here are some skills that are going to be particularly important for this lesson, so go ahead and warm up those skills. Pause the video and come back when you're done. What this video series will be about is all polynomials that are degree 2. In other words, we're going to look at quadratic equations and quadratic functions. So anything that is degree 2 is what we will be hitting in this video series. If you recall your lessons on linear functions, you will remember that there were 3 forms of a linear equation. Well, quadratic functions have 3 forms as well, and the one we'll stick with in this video is the standard form of a quadratic function, and it looks like this. Now, in this standard form, A, B, and C just represent the numbers that would be located there. And then you will always have this in, again, standard form, which you've heard of before, descending powers. So you have a squared, then you have your x term, and then you have a term with no variable. So your quadratic functions that you'll see throughout this chapter, you can tell are degree 2. This is a monomial, a binomial, and a trinomial, but they're all degree 2. And then over here, I'm just reminding you that you might see f of x instead of y. Remember, f of x is just function notation, but it really means y. And always keep in mind that all we're doing is looking at the polynomials of degree 2. So we're specifically looking at quadratic equations. So we're going to look at our parent function for our first quadratic equation. And the parent function is this one you see right here. Y equals x squared. Remember, a parent function is just the most basic function in that function family. So let's see what a quadratic equation looks like when you graph it. If I put in a negative 2 in for x and square it, remember all of negative 2 gets squared, and so you end up with a positive 4. If I substitute a negative 1 in for x and take a negative 1 times the negative 1, you get a positive 1. Putting a 0 in gives me a 0 out. Putting a 1 in and squaring it gives me a 1 out. And putting a 2 in and squaring it gives me a 4. And you need to remember that when you make these tables, you're just creating coordinate pairs that can be graphed on the coordinate plane. So I will go ahead and graph these at negative 2 and 4, negative 1 and 1, 0, 0, 1, 1, and 2, 4. And this shape here is very important. It goes up forever in that direction. This shape is called a parabola. So when you graph any quadratic equation, you will end up with a parabola. It's important to note that this is a curved edge down here. I didn't do it so great on this, but it's a curved edge, not a hard corner like it would be for an absolute value function. So let's look a little deeper into this parabola. Again, a parabola is this U-shaped curve, and then it has a specific point that we need to point out, and that is called the vertex. The vertex is either the highest or the lowest point of your parabola. So in this picture, it is the lowest point right here. That's called your vertex. And maybe you notice that we could cut this parabola in half, and if we were to do that, it would have a mirror image of itself. And we call that line that can cut it in half the axis of symmetry. So for this equation, or this graph, you can see that your axis of symmetry, I'll have to move it, is right here. That is the line that would cut this parabola in half. And please notice that your vertex is on this axis of symmetry. Because axis of symmetry is so hard to write out, because it's a long phrase, we might abbreviated AOS sometimes. So that's axis of symmetry. In these two examples, we're just going to write the coordinate pair of the vertex and then the equation for the axis of symmetry. And it's important that your forms in which you write these are accurate. A vertex is a coordinate pair because it is a point, and your axis of symmetry is a vertical line. And so if you remember, vertical lines always have the equation x equals. So make sure you write it in the proper form. Let's look at the vertex of this first one. It is the lowest point of this parabola, which is about right there. And so the vertex would be the coordinate pair 0 and -5. Your axis of symmetry then again is the line that cuts this parabola in half. It also contains the vertex. So x equals 0 is this axis of symmetry equation. Looking at the second one, our vertex seems to be right here, and so we would need to count to figure out where that coordinate pair is. I counted over to the left 5, and then to get to it I'd have to go down 1, 2, 3, 4, 5, 6, -6. So vertex is located at -5, -6. And then again your axis of symmetry. We'll cut that parabola in half. Important to see that your vertex lies on it, and so that will be x equals -5. And it is no trick that your axis of symmetry is the x-coordinate of your vertex. That is something you should realize is associated, because if your vertex lies on your axis of symmetry, it makes sense that your x-coordinate would be your axis of symmetry location. This example, we're just going to sketch backwards, where I'm given the vertex and then the axis of symmetry. Again, notice that your x-coordinate is the location of your axis of symmetry. So if I was told that this parabola is located at -5, 6, you would count over 1, 2, 3, 4, 5, and then up 6. 1, 2, 3, 4, 5, 6. It's about right here is where my vertex is located, and then you would simply draw in your parabola. We're just kind of playing pin the tail on the donkey right now, so we're not really sure how wide or narrow our parabola is, but we're just making sketches. I'll have you guys try this one. Your vertex is located at 3, -4 with an axis of symmetry logically at x equals 3. So pause the video and try to figure out where this parabola goes. And I have mine located right there. Remember, your vertex is the lowest point of this parabola in this case. So we've mentioned several times that your vertex can either be the lowest point or the highest point of your parabola, depending which direction your parabola is opening. And so we give that specific vocabulary names. If your vertex is the lowest point, as it is in this one right here, we call your vertex a minimum, because it is a minimum value that you will have for your y-coordinate. It's the lowest or smallest that parabola will get. Then the opposite can happen. If your parabola is opening down, and that will happen if you have a -a value, we call it opening down. I know that sounds funny, but if it is opening down, then your vertex will be the highest point, and so we would call our vertex in this situation a maximum. It is the maximum y value you will get for that equation. So hopefully up to this point you've done some exploration with quadratics and how they behave based on their equation. And so we're going to start translating or moving our parabolas. It just means moving them around the coordinate pair according to whatever the directions are. And this one says that we're supposed to translate our parabola up 3 units. And so what that means is our entire parabola is shifted up 3. So if you start at the vertex, which was at 0, 0, and move it up 3, you're going to end up with your parabola shifted up here. And then every point on that parabola is shifted up 3. That's really horrible. But your parabola is now located here. And so that was a vertical slide, we can call it, or a translation up 3 units. Here's a parabola whose equation is listed right here. It's y equals x squared plus 1. And you have already learned that adding this plus 1 shifts your parabola up 1 vertically in that direction. And now they're asking us to translate it left by 2 units. And so you would take your parabola, and I always start with the vertex, and move it left 2 units, and then this was from here to here was up 1 over 1, so you would just copy that behavior. So the final location of this parabola, translated already up 1 unit, now is translated left 2 units, and so the final parabola location would be here. Remember, it's always what are we doing to the parent function based upon what's being added to it or subtracted from it or multiplied by it. So again, hopefully you've done some exploration with quadratic equations on GeoGebra or Geometry Sketchpad, and you already know what the numbers do to the parent function. So based on that, we're going to start with the parent function, and we're going to write a new equation for each of these. And so I will walk you through it to see what the equation looks like. So the first one says that our new equation has our parabola shifted down 2 units. Well, remember that's a vertical motion, and the vertical movement of your parent function comes from adding or subtracting a number to your x squared value. And so we would write x squared minus 2 as your parent function shifted down 2 units. Now left and right movements are different. Remember, those are inside parentheses. And so if I move my parabola right 2 units, I would have to write x minus 4 squared inside of a parenthesis. And this is kind of counterintuitive to how you think it should move, so you have to be very careful about that. But if you make a table, you would see indeed that because of this squared operation that this truly does make sense. So a parabola that is shifted right 4 units will have x minus 4 inside parentheses. Left 3 units, that again goes inside the parentheses. Remember, horizontal movement happens inside parentheses, and left again is counterintuitive, so that would be a plus 3 for 3 movements left, and then squared. And in this final one, we have them put all together. So up 5 units and left 2 units. I'm going to stop talking, and maybe you can write down what you think the equation would look like. So give it a try. So if this was moving up 5 units, I already know I'm going to have a plus 5 on the outside of that parenthesis. It's just kind of like a y-intercept. Inside, because I'm moving left 2 units, I'm going to have a plus 2. That's that opposite idea, and then that whole thing squared.